Okay, so hi to everyone. I'm Sara Dubbioso, and I'm a postdoc working with the CREATE group at University of Naples Federico II. Today I will talk about data-driven and model-free approaches that we studied in the past years to tackle the magnetic control problem. First, I will give you a little bit of insight of how we want to use AI for the magnetic control task, especially like from a CREATE point of view, so how we deal with it. I will give you some information about the activities that have been done. Specifically, I will present you an extreme-seeking algorithm applied to the vertical stabilization enhanced also with the use of neural network. And then, of course, reinforcement learning agent applied both to the vertical stabilization problem and to the shape control. At the end, I will draw some conclusive remark, especially comparing pro and cons of using reinforcement learning agents against traditional controllers. So how can we use AI for in the magnetic control? ML structures, or basically neural network, can be used to replace the models that we usually use to represent the plasma exoranic structure behavior, or more specifically, use neural network to extract information from the plasma, to extract information about the plasma state or the behavior of the plasma inside the vector, and then this information can be passed to a controller that then can act on it in order to obtain some model-free solution. We will see actually that the extreme seeking is one of this kind. And then the reinforcement learning agent that in our case, we treat a little bit differently, was already mentioned the big work on the magnetic control of TCV, and there was just one big agent, reinforcement learning agent, solving the whole magnetic control problem. We try to do something different. So basically, train the agents to solve single control task inside the magnetic control problem for every tempo of the vertical stabilization. So let's go into some more details. As I said, we studied a model-free approach to vertical stabilization using an extreme-seeking algorithm. And we will see how we included also neural network inside this control loop. Let's say that this architecture was developed for the ITER case, so for the vertical stabilization on ITER. Now there is the plan to test this also on a real machine on TCV specifically. Considering the URL approach, we started back in the years in 2021-22 using developing a simple tabular co-learning algorithm for the vertical stabilization of the East tokamak. Then we did some step forward and we go to deeper reinforcement learning with the DDPG agent developed always for the vertical stabilization case for the ITER tokamak. And then we have some work on the shape controller where a model-based controller, basically a PI and a DPG agent, were combined and tested on demo. This work was done by colleagues from the University of Partenopei and Vanvitelli. So, starting from the extreme seeking, what is extreme seeking? It's basically a switching control law. As you can see, we are applying a switching control law with a cosine function. That can achieve stabilization of an unstable plant, in our case, the plasma, minimizing a candidate Lyapunov function of the plasma state, of the system state. We choose as Lyapunov function the movement of the plasma state along the unstable mode. And in the first step, in order to estimate this value, we used a Kalman filter. Even if we proved to have some robustness using the Kalman filter, because our approach was to use the same Kalman filter even if the plant was changing. So even the configuration of the plasma was changing, there was still some model dependence because of the Kalman filter. Why I'm stressing the things about model dependent and why we want this approach to be model free, because tokamaks are running, like discharge are running also with elongated plasma, so the vertical stabilization problem is quite understood and solved. but the controls used are model-based controls. So the parameters of these controllers are tuned based on the plasma configuration of the specific model of the plasma we are considering. If we change the plasma configuration, if the model changes, we have to retune also this controller. So in order to avoid this, we want some model-free solution. So some controllers that does not depend on the models, and so can be used through all the different discharges. In order to do so, and to remove the model dependence from the Kalman filter, we replaced the Kalman filter with a neural network that was trained using the same inputs that the Kalman filter was receiving, and that was giving an output movement of the plasma along the unstable mode. This process, as in general, the training of the neural network was kind of time-consuming. First of all, remember that ITER is not working, so we don't have data from ITER. In order to obtain the data to give to the neural network, we had to run synthetic shot. And then in general, to train neural network, there's always this trial and error process in order to tune the hyperparameter of the network. That is kind of not deterministic, like you choose the value of a parameter, and then to understand if it's the correct one, you have to train your network and see the output. But however, with the neural network, we obtain better generalization than we expect with the Kalman filter. Here is an example of equilibrium-free plasma configuration where both cases were working, and here is reported the vertical position of the plasma centroid, and we see that at the beginning of the simulation we have some displacement, and then is compared to the behavior that we obtain using the extreme seeking configuration with the Kalman filter, and then the result that we obtain using two different neural networks, a vanilla multi-layer perceptron and a more complex extreme learning machine, and all of this also compared with an ITER-like vertical stabilization, which is a model-based, which is the classical model-based one used in the CREATE group. Here I reported 3 examples where all these approaches work, but there were also some cases where the approach with the Kalman filter and the ITER-like were not working, while the same neural network can be used to stabilize more than this equilibrium situation. Going to the reinforcement learning, as I said, our first approach to this field was with a tabular, super easy Q-learning agent. What we have to focus here is the reward function. The reward function reflects the objective of a BS controller, specifically to stop the motion of the plasma, so bring to zero the velocity, not the position. The position is then recovered together with the shape controller, and then to minimize as much as possible the current in the BS coil. Usually are in vessel coil, so you want to keep the current as low as possible, as well as the control voltages. In this case, we didn't include the other control loop, so the shape controller and the plasma current controller during the training, even if they were then considered during validation of the Q-learning agent we obtained. So this is also some kind of robustness. We did a step further. We used deep neural network with a DDPG agent, in this case applied to the ITER vertical stabilization. In this case, we consider a more complex environment since also the other magnetic control loop, shape controller, and plasma current controller were included in the training environment. And we try to do also something more specifically to understand which is the impact of the hyperparameter on the training and on the control performances. So once we obtain like the perfect training, we then try to change some of the parameters, for example, the episode duration, the decay rate of the noise, or the dimension of the network, to understand what was the difference between using these different hyperparameters. Again, the reward function is similar as before, but in this case, we had to tune also some of the weights. We did also some tuning on the weights of the reward function, specifically on the weights on the current in the BS circuit, specifically because with a low value of this weight, we could not achieve to have zero current at steady state, so when the position is recovered. So we had to increase this gain, or even more, penalize also the integral value of the current. Then last approach that I will present is the hybrid model-based, learning-based architecture for the plasma shape controller. In this case, we have the two controllers contributing together to track some error on the plasma shape. But again, as I said before, like the training of neural network, the deep learning agents are time consuming. Time consuming also if consider the training time. For example, for training these agents, it took around like 24 hours. But here's some results. The simulation was done basically moving the plasma to close to the insider wall, giving some displacement to some of the gaps. And we can see that here, if we use the data-driven control and combine it with the model-based one, we can obtain like small tracking error and better control performances. So finally, let's draw some conclusion on this. Again, I repeat, like using reinforcement learning agent or in general neural network, a time-consuming and resource-consuming activity. First of all, because we required a large amount of data, interaction data. Just remember that, for example, for ITER, we had to run a synthetic shot in order to obtain the data because they were not already available. But even if we are considering working data from a working tokamak, then this data needs to be collected and pre-processed because you cannot give raw data in input to the neural network. And then there's all the process of tuning the ITER parameter. That is basically a trial and error process. There's nothing deterministic on this, and also the reward function. Reward function is very important to design correctly the reward function because poorly designed reward function can lead to suboptimal solution, and so also to dangerous situation, dangerous solution that for a fusion environment can be quite critical. And as I say, there are also other laboratories, other labs that are doing activity with Prey, Selective Mind, and so they were able with like the resources, the structure, the people, the expertise, all working on a single task to finally obtain like a bigger result than the one we can obtain by running basically this training on our server or computers. Indeed, this is a reference taken from the paper published on Nature, and they have just one agent that could control the plasma also with different shape, double null, negative triangularity, with just one reinforcement learning agent. Sorry. And then the single reward function is kind of a pro for the case of reinforcement learning, because what also has Adriano presented before, which is how the magnetic control problem is tackled. Basically, it's divided in different sub-problem, in different control loop, and for each control loop, separate controller are designed for the plasma current controller, the shape controller, the vertical stabilization. When we use reinforcement learning agents, especially in the case of one agent solving the whole magnetic control problem altogether, there is just one reward function that takes into account of everything, including nonlinearities. But the last point, I think also the more important, is that these reinforcement learning agents are basically black boxes. There are no clear relation between the parameters in these AI agents and what will be then the control performances. And this is not true in standard controller. We know that if we put like some integral action in our controller, then we will have zero steady state for some quantities at the end. And this is kind of, or this is known, this is sure. But with reinforcement learning agents, the agent can learn some policies that may also have like some unexpected or unsafe behavior if the agent will find himself in some situation not seen during the training, which is something different from classical controller, because in general, there was a lot of research in the past year, and so the stability of classical controller is well understood, so we will know what will be their behavior in off-normal condition. And then, of course, something that I did not put in this slide, like if we have to run in real time our neural network, the cost will be quite different between running a classic PI, for example. So I think like the big question now is, do we trust this reinforcement learning agent to run on fusion machine like ITER or demo? And I think right now maybe the answer is no, but this does not mean that we have to stop working on this or researching on this field. Since, as also Adrian said before, maybe the solution is to combine AI machine learning models and classical controller, or even to find some new solution. Just keep researching on this. This is also a cutting edge approach. I'll leave you with some references of the work I've been presenting during this talk. I don't know if you have some question. I will be happy to answer.
Yes, thank you. Thank you very much. I don't see any questions submitted, but I have a question from myself and my team. You mentioned that reinforcement learning is a black box. Do you think that AI approaches are completely not applicable for fusion because they are, at the end of the day, most of these neural network are black boxes with difficult to trace?
No, like they have a huge breakthrough applying reinforcement learning agent to TCV, but TCV is a small machine, very flexible. So it would be different to apply these approaches to some like research machine to real tokamak that we want to use to generate fusion. Like if we have some problem with ITER, we can have real damages. Maybe we have to shut down the machine. That's not safe thing on TCV or D3G, for example. And then still, there will be some years until we see ITER working. And I think keeping researching on this, keep researching on things that are cutting edges like AI, maybe will bring us to a path where these technologies will be also applicable to such a machine. Maybe researching and studying, we will find also some stability proof also for AI models. Who knows?
1 second, someone sent a question. Theo is asking about the question of trust. How do you foresee the increase of explainable AI that affect that? Is there something applicable for your model as is, or with minor changes? So basically, the obvious question about like what kind of explainable AI or explanation could convince you or ITER to use AI and ML?
I think from my side, from my experience, to understand what the parameter does. So that's why in the DTPG approach to the vertical stabilization of ITER, what we try to understand is what, if I change this parameter, what happened? If I change this other parameter, what happened? If I change the weights on the reward function, what happened? So try to understand better what the things that we can control. So this hyperparameter will affect our control performance. I think we have to investigate better on this, because right now the sense that I have is that yes, at the end we found a solution with reinforcement learning, with neural network. At the end we are able to do it because they are very flexible, they're very powerful tools. But in order to obtain the how do we know that we obtain the optimal structure? That you don't know. Maybe I found a solution that works, but maybe it's not the optimal. So I think we have to keep working on that.
Okay, that sounds good. Thank you very much. That's it on the questions, and we will pass the stage to Václav with a closing presentation.